In this class, we are going to see another very important perspective of the Dirac theory, the Dirac Hamiltonian of electron. We will check, as our experience in non-relativistic quantum mechanics, whether the angular momentum commutes with the Dirac Hamiltonian. We note that, say, the z component of angular momentum commutes with the non-relativistic Hamiltonian of a, say, free particle. H in R is the non-relativistic Hamiltonian, and our knowledge says that for non-relativistic Hamiltonian, Lz commutes with the Hamiltonian. If you add a central potential, then also the angular momentum commutes with the Hamiltonian. We have written only the kinetic part here, as we are considering the free particle. In Dirac Hamiltonian also we will consider the free particle. The Dirac Hamiltonian is, as you know, C into alpha dot p plus beta m naught c square. M naught is the rest mass. Alpha x, alpha y, alpha z are compressed here. They are matrices. Beta is also matrices, and we are going to check whether the z component of orbital angular momentum, it commutes with the Dirac Hamiltonian. Dirac Hamiltonian is denoted as Hd here to separate it from non-relativistic Hamiltonian, etc. So let us now expand Lz and Hd commutation. We can also do in an exactly similar way Lx commuting Lx and Hd commutation, Ly and Hd commutation. In a similar way we can calculate. So you now write Lz as x py minus yp. These are all known things. Just you do the calculation. You will have these notes in your hand. You can download it, and so just go on calculating as usual. And this is the Dirac Hamiltonian Hd. Now we expand alpha dot p and do all the commutations, and you see that only these two commutations survive. X py and c alpha x px, they will survive, minus this y px with c alpha y py will survive. This is why note that x and px, their commutation is not zero from uncertainty principle. Similarly, y and py, their commutation is not zero from uncertainty principle. All other commutations will be zero. You can check, because you know that px, py and pz, if you select any two, then their commutation will be zero. Px commutes with py, py commutes with pz, pz commutes with px, and so on. And alpha and beta, they do not depend on xyz and pxy, pz. So all the commutations will be zero, except these two commutations, they will be non-zero due to the uncertainty principle. You go on and check this expression, and now you expand it. Just you will find it like this, and the final expression will be ICH cut alpha x py minus alpha y px, which is necessarily not equal to 0. Similarly, Lx and Hd commutation will be a similar expression, that just you change xyz in a cyclic manner, and it will be not equal to 0, and Ly also will not commute with Hd, and this is the result. Thus you see that Lx, Ly, Lz not commute with the Dirac Hamiltonian. That means they are no more. This is not more. This actually this is no more. They are no more conserved according to Dirac theory. So they are not constants of motion, and so L is not a conserved quantity. This will be Hd, you note, Dirac Hamiltonian. So L is not commuting with the Dirac Hamiltonian. So this is now very past in situation. angular momentum is not being conserved. So there must be something fishy, because angular momentum is a very fundamental quantity, is remain conserved. So what is the problem? The problem may be from two angles. One is there any problem with the Hamiltonian? And another problem is our angular momentum complete enough? Have we considered angular momentum from all possible considerations? So what is the appropriate angular momentum expression that commutes with HD if we consider that our HD is correct? And it is correct. Just check, we calculate this commutation alpha x and alpha y, alpha x into alpha y, commuting with HD. Just you go on calculating this, you write your HD, and first you check the commutation with beta and expand the commutation. Just you do not disturb the right side term, that means the minus beta alpha x alpha y, just keep it intact. Just you change this alpha y beta as minus of beta alpha y, because you know beta anti-commutes with alpha y. Alpha y beta plus beta alpha y equal to 0. So alpha y beta equal to minus beta alpha y. You know this. And then you pick this term alpha x beta equal to minus beta alpha x. So this minus sign is absorbed here, becomes plus, and finally it becomes m naught c square beta alpha x alpha y minus beta alpha x alpha y equals 0. So your alpha x alpha y commutes with beta m naught c square, or say alpha x alpha y commutes with beta. And exactly in a similar manner you can show that alpha x alpha y also commutes with c alpha z pz. That means c alpha z pz is the third term in your commutation expansion. Alpha x alpha y commuting with c alpha z pz. That means these two terms, they commute with alpha x alpha y. So you need to calculate the commutation with alpha x alpha y with c alpha x px plus c alpha y py, and you now calculate. So alpha x alpha y commutation with HD comes out to be these two commutations, and you just expand alpha x alpha y and alpha x px, alpha x alpha y alpha x minus alpha x square alpha y. You just do it. I am not reading this out. Your px will not be disturbed, because px has no dependence on alpha x and alpha y. So you can involve it or you can ignore it. Your results will be unchanged. So here px, and in the second expression it is py, they will be not changed. C is taken common and it is put out of the third bracket. And so finally if you do the calculation, it comes out to be 2c alpha x py minus alpha y px. Now this is a very interesting expression, and you can write in other way that alpha x py minus alpha y px equal to 1 by 2c of commutation of alpha x alpha y and ht. Just use this relation, this left hand side this one and right hand side this one. So alpha x py minus alpha y px equal to 1 by 2c alpha x alpha y and ht commutation. Now we have already proved that LZ commutes with HT. We have already proved that LZ and HD commutation relation is equal to IH cut C alpha x py minus alpha y px. Now replace this alpha x py minus alpha y px from this relation. So use the expression from 2. So LZ HT is minus IH cut C to 1 by 2C, this commutation. Now you cancel this C and bring the whole commutation in the left side. Just I have added a note at the end of the page. If we have A commutation B equal to C commutation B, like here, LZ commutation commuting HD and this one commuting with HD, then bring this one in the left hand side. So A minus C will commute with B. So use this one here. You will find LZ minus IH cut by 2. This C cancel out. Alpha x alpha y. These two quantities commute with HD. LZ minus IH cut by 2 alpha x alpha y whole together, it commutes with HD. LZ separately is not commuting with HD, but in conjugation with this one, when you mix these two, when you add this part with this part, it becomes 0. So exactly similar, you change the indices x, y, z and Lx with this relation alpha y alpha z, Ly with this alpha z alpha x, they commute with HD. So these expressions Lx minus I h cut by 2 L alpha y alpha z, similar for Ly, similar for Lz, these quantities are constants of motion when you consider the Dirac Hamiltonian. Now what happens? Let us do some simple algebra. Just no algebra actually here, it is just simple substitutions. Let this I alpha y alpha z, I alpha y alpha z minus sign included as sigma x. Let sigma x equal to this. I have put capital sigma here just to so that you don't get mixed them with Pauli matrices. Remember Pauli matrices, sigma, small sigma x, small sigma y, small sigma z, they are of 2 by 2 dimension, but as alphas are 4 by 4 dimensions, these big sigmas, capital sigmas, are of 4 by 4 dimensions. So be very careful before choosing the symbols. So capital sigma is equal to minus I alpha y alpha z. Similarly, sigma y equal to this one, sigma z equals this one, and you check that when you square them, they become 1, 4 by 4 unit matrix, and sigma x, sigma y plus sigma y, sigma x becomes 0. That means they anti-commute, and same for other components, sigma y, sigma z plus sigma z, sigma y equal to 0, and so on. Now if you calculate this commutation, sigma x, sigma y, put everything here, then do some jumbling, and you find out to be sigma x, sigma y equal to 2 alpha x alpha y, means 2I sigma z. Just check here, sigma s commutation sigma y is 2I sigma z. Now you couple half h cut here, because half h cut is left here, minus I alpha y alpha z, this is known as sigma x. So what is left? H cut by 2. So you couple here h cut by 2 sigma x and h cut by 2 sigma y. So it will be here half h cut I sigma z. So in a general way, by using the tensorial notation of Levi-Civita symbol, so half h cut sigma I, half h cut sigma j equals half h cut epsilon ijk sigma k. This means half sigma x into h cut, half h cut sigma, h cut sigma j satisfy the angular momentum algebra. This is the they follow the angular momentum algebra with j equal to half. That means they correspond to the spin half case. So from Dirac algebra, when we try to check whether there is what is the angular momentum component which commutes with the Dirac algebra, it gives us directly the spin half case. That means electron spin comes directly in the Dirac algebra. So let us now use half h cut sigma s x as sx, sy half h cut sigma y, sz equals half h cut sigma j. You define now your jx as lx plus sx, jy, jz defined this way, and you see that jz commutes with hd, jy commutes with hd. We have already checked this, just now symbolically we write. We have checked it in the previous part here. Actually this is nothing but jx in our new symbol. This is our jx, this is our jy, and this is our jz. So now we use jz commutes with hd, jy commutes with hd, jx commutes with hd. That means j, the angular momentum operator, commutes with hd. Just a recap, remember that this is our expression that commutes with Dirac Hamiltonian, and we write it as jz. This is the total angular momentum, that is the heading there. Jz, the total, the z component of total angular momentum, not only the orbital angular momentum, but the total angular momentum, z component of total angular momentum, that commutes with the Dirac Hamiltonian. So the Dirac Hamiltonian directly introduces the electron spin. We do not need to consider the spin of electron in an ad hoc manner as we have done it in non-relativistic calculations. The spin of electron comes directly in the relativistic formalism through the Dirac Hamiltonian. We end here.